To remind you about that. So do you remember, what did we have to do to see that screen fluoresce in the X-ray room when it was energized? What did we have to do? We turned off the overhead lights. What else did we had to turn off the lights inside the room. The indicator light that we made an X-ray exposure, I had to cover that up, right? And did it glow brightly? Were you like, oh, look how bright it did? It light up the room? No, it was very dim, right? So how can we make the screen? In fact, I don't know if you remember, but do you remember when we were making the exposure? Was it you or Mr. James? Somebody was doing the exposures, and we had to let the machine cool down. I had it up as high as it could go to make that screen fluoresce. Not as high as it could go, but we made a couple of exposures, long exposure times, high MA, and it was getting cranky because it wouldn't expose again until the anode cooled down a little bit. So that was a lot of exposure onto those screens, and you saw how dimly they lit up. Okay, so that was a problem with these, just looking at the screen glowing. Remember, the radiologist had to have the room darkened. Only one person could look at that screen glowing. So what was invented to help us? When do we see better? We see better with lights on. Mm-hmm. And so trying to get the image to glow brighter so that we can see it better with the cones of our eyes. So what was invented was an intensification screen. Intensifier tube. Okay, and this is basically, we're going to go over this a couple of times. Again, this is your classic setup. The X-ray tube or the fluoro tube is underneath the table. X-rays come up through the patient. This is the image intensifying tube right here. I love the name. The name, it's a great name. We're intensifying the image. We're making it brighter. We're making the image brighter. So if it is brighter, we're able to see it better. So this is the image intensifier tube. The X-rays go, you can imagine the screens are in here, and then the image is projected on the other side of the image intensifier tube, and then it goes to our computer monitor that we see the image. So now we're looking at a monitor, a computer monitor, and you can certainly see those with the lights on. So with image intensification, these are the advantages of having it. And the main thing is that the image is brighter. That was the whole purpose of it. Now, it says photopic vision can be used. Photopic, and I think I talked about this a little bit last time. You're using photopic vision right now. The lights are on. We're using the cones of our eyes. That's daylight vision. Can you not see better in the daylight than you can in the dark? Of course. Nighttime vision is the photopic vision, which we'll talk about again here in a second. Now, with looking at the image on a monitor as opposed to a screen, more people can view that. So more people, as in the most important person would be you as a radiographer, you can tell during an upper GI if the stomach is long and J-shaped, if it's high and transverse, that sort of thing, so that you can help, that will help you with your imaging if you need any after the exam. And plus, it's interesting. Can you imagine watching the radiologist look at a screen? Here's a radiologist, at the table, patients on the table, and the radiologist is looking at the glowing screen. And you're over there doing what? Getting the barium when the doctor needs it, or whatever. So now everybody's looking at a monitor. Even, if you're not doing it, at least you can look at the monitor. What can the patient do? They can look at the monitor maybe, depending on where it is. So multiple people can see it, and it just makes it more interesting. Overhead lights we usually dim them, don't they usually dim the lights during the procedures, or do they keep all the lights, overhead lights on? Whatever the radiologist prefers. A lot of times we kind of do it like this, but overhead lights can be on. And then again, they don't have to dark adapt. Since we're using our cone vision, we don't need to dark adapt the eyes to a darkened room. So lots of advantages. This is a picture, this is out of your textbook, And this is just showing you the basic setup, where again, the image intensifying tube is up above and the fluoro tube is underneath. And then the X-ray tube that you use to take routine radiographs with is usually moved out of the way. And so you have 2 X-ray tubes in that room, one underneath the table, and then just like in our lab, in our back room, in our Phillips unit. So again, looking at the eye, again, here are the cones that are towards the central portion, the posterior portion of the eye to the center portion. So you can look at the monitor, at the image direct, as opposed to what the radiologists did in the olden days. Previously, they used the rods, your nighttime vision. Remember, again, the room was dark, lights were dimmed, and so the radiologist was looking at a screen, a glowing screen, and so they had to use their peripheral vision to see the image. That takes talent, a little bit, in practice. Astronomers do the same thing. They don't look directly into the telescope. They look and use the peripheral vision because that's where the rods are and they're looking at night. So they actually do better with that. So with image intensification, the cones can be used. We can see better. With that. So some terms that I want you to know are these, and they're pretty basic terms. They're not very hard. Visual acuity, the ability of the eye to perceive fine detail, contrast perception to determine different brightness levels, and then integration time of the eye is 0.2 seconds. Now, what does that mean? So this is an important concept with fluoroscopy. Fluoroscopy is where you're going to get your higher readings, not high readings, higher readings in routine radiography. Where are you when you took that foot X-ray?
Behind the shield.
Behind the shield, kind of outside of the exam area. So in fluoroscopy, we tend to be in the room or going into the room maybe during the fluoro procedure. So our fluoroscopy energies are still low. However, you're going to get more of a reading if you do a lot of fluoro exams. So what can we do? Everything we teach you in fluoroscopy pertains to radiation protection for you and the patient. Huge. And you need to know everything that you need to do to protect you and the patient. So one thing is the integration time of the eye. So it's 0.2 seconds, 1/5 of a second. In radiology, that's kind of a long time. It's 0.2 seconds. Okay, so what that means is whatever your eye sees in 0.2 seconds is what it's going to see. The image doesn't build up, it doesn't get clearer, it does, if you can't see it, I'm looking at that poster on the far wall. I see active shooter and I can see run, hide, and fight. Me too. Okay, I can't read anything else, and looking at it all day long, I cannot do, nothing's gonna change. I still won't be able to read it 5 hours from now, standing here, right? Whatever I see in 0.2 seconds is all I'm going to see, okay? Unless I do something different. I can move up to the poster and go, oh, yeah, I can see it. I can stand back there, make the poster bigger. I can read it then. Okay, so when a radiologist is looking at an image on a monitor and they're having trouble visualizing it, we have to do something different. They have to do something different, or we have to help them do something different. Bring the image intensifier tube closer, bring the monitor closer, increase the KV or the MA to make the image brighter. Something has to be done, but sitting there looking at an image, not being able to see what you need to see and still fluoroing is not acceptable. That just gives excessive radiation exposure to the patient and to the person, to the operator. Okay, so the integration time is important. And when we do take a test on this, you'll have these definitions. I'll ask, what's the integration time of the eye? What is the ability, what term is the ability of the eye to perceive fine detail? So know your definitions as we go throughout. Okay, those are pretty easy enough, I think. Okay, so this is the different parts of the image intensifying tube, and I want you to know the parts of the tube and the purposes of each. So looking at this, let me orient you. So the patient would be down here, okay, laying on the table, and the fluoro tube is underneath that. Again, in the classic example, there's a variation to that, but just for now, the fluoro tube is coming up, radiation through the patient. So now the X-ray photons have been attenuated and some go on through. This is the exit beam right here from the patient going in to the image intensifier tube. So the first thing that we have is input phosphor. So there's a screen right here. Okay, so that takes the X-ray energy, absorbs it, and then emits light energy. Okay, so what's the purpose of the input phosphor? X-ray energy to light energy. Does the phosphor absorb 100% of the radiation? No, they never do. There's not a phosphor that's 100% effective. Okay, so then right next to that, okay, so what comes out of the phosphor is light. You see the light here? Okay, this, you have a picture like this in your textbook. This is a different picture, but you have it on your PowerPoint. So here's the light here. The light hits the photocathode. What do you think the photocathode does? What does photo mean? No, not a picture.
Light, right?
Yeah, light. Yeah, not a photograph. A photograph is made with light, so that's why it's called a photograph. Photo refers to light, and so cathode is your electrons. So it takes, the photocathode takes the light and converts it to electrons. Now we're looking at, they call them photoelectrons or electrons, either way. So the photoelectrons are now being guided and attracted to the anode, right? The anode is positive, electrons are negative. Okay, in between we have these electrostatic lenses that help focus the electrons. Otherwise, electrons next to each other, what do they want to do?
Scatter.
Yeah, they want to get away from each other. So we don't want the electrons to go further out. We want to keep them narrowed. So we have these electrostatic lenses that help draw and propel the electrons to the anode. Now, the electrostatic lenses are positive so that the electrons will, and you can see them coming a little bit, narrower and narrower and narrower to bring the beam in closer, the electrons closer to each other. You don't have to know these numbers, but the potential difference on the anode is about 35 kV, so very low for what we use in radiography purposes. 35 kV. These electrostatic lenses might be 10, 15, 25, 35 up to the anode. So each electrostatic lens has a higher potential difference as it's drawing the electrons out. So they get to the anode. Notice that the electron emitted here crosses over to the other side, and then we have the output phosphor. So this is a screen on the other end. So these electrons hit the output phosphor. That output phosphor takes the energy of those electrons and absorbs it and does what?
Converts it back to light.
We end up with light again. Okay? So we had light down here and light up there. Notice that the electrons, as they come from the input phosphor, they come up and they cross. This is the focal point. They cross and then start to diverge again. So kind of crazy, right? I mean, we have light here, we have light there. Why don't we just forget all this and just have light? Well, that's what we started out with. That's what it was. Piece of cardboard with that phosphor on it, and we got that light. What we want is this light. Can you tell by just looking at that what would make it better? Do you think the light here is the same as the light here?
Is it because it's more condensed now?
Very good. It is. It's more condensed, right? You have a flashlight and you have a big area. What happens when you bring that flashlight closer to the table? the area gets smaller, and what happens to that light intensity? It gets increased. Yeah, it's increased. So that's exactly how an image intensifier makes that light more intense or brighter. There's some other things, but that's one of them. So I have a little YouTube somewhere. How do I put this up? It's a real short one. Why isn't it?
This animation demonstrates the principles by which all X-ray image intensifiers operate. The X-rays arrive at the input window, where they are converted to a stream of electrons.
I'm sorry for this. It's sideways. The one I was showing you before was like that. Okay, so if the table were standing upright, the patient would be here, the fluoro tube here, patient here. That's your X signal.
Which can be accelerated towards the anode by a high voltage and focused by electrodes positioned along the path. At the anode, they strike a phosphor screen and are converted to light, which is captured by film or CCD camera. Let us now look more closely at the input stage. Here, we see the X-rays entering the scintillator cells, in this case cesium iodide, where they are converted to photons at the frequency of visible light. These photons strike the photocathode, causing electrons to be released. The benefit of the image intensifier is that the signal intensity of the X-ray beam can be amplified through the selection of scintillator, the magnitude of the high voltage, and the nature of the focusing components, which control the electron stream, and then the sensitivity of the phosphor screen and of the image capture device, which are now operating at visible light frequencies.
Okay, so just a little, I don't want to watch that. Wait, stop. Okay, so this slide, and you have it on your PowerPoint, shows the different parts with the purpose, and I'm certainly going to ask you questions about that. So a couple of things that we did not talk about in that previous slide was that the image intensifying tube is a glass tube, and it is surrounded by metal. Now, if you've been in our back X-ray room, the Phillips room, and you see the image intensifier tube is covered actually in plastic if you were to hit it. But on the inside, that's just a cover. The inside of that is metal, and then the inside of that is the tube. So it's just like an X-ray tube that has a vacuum and is covered by metal, except for where we want the X-rays to come out. The image intensifying tube, and we call it the II tube. So when you see II, that's image intensifier. It looks like the Roman numeral 2, but it's the II tube. So the glass, or if it's made out of metal, a lot of the newer II tubes are made out of metal. That's just like an X-ray tube, is to provide a vacuum. We don't want any air molecules interfering with those electrons coming across from the input phosphor to the output phosphor. And of course, the metal housing, unlike the X-ray tube, we're not producing X-rays in there. Now some X-rays are in there, but we're not producing X-rays, so the metal is just to protect the tube itself. Okay? So it's different. That part is different than an X-ray tube. The metal on an X-ray tube is to absorb the radiation coming out the top. Input phosphor, we talked about that. And it doesn't really convert. It absorbs X-ray energy and emits light energy, but we use the word converts just for convenience. CSI, as you saw in that video, is the phosphor that we typically use for our input phosphor. The photocathode takes that light energy, converts it to electron energies. The anode attracts the electrons. There is the output phosphor. I'm skipping the aluminum just for a second. The output phosphor takes those electrons. So the output phosphor is a little bit different than the input phosphor in that it takes electrons and converts them to light, whereas the input phosphor takes X-rays and converts to light. Typically, it doesn't have to be, but typically zinc cadmium sulfide is the phosphor at the output phosphor. There is usually a thin piece of aluminum. In my current readings, it could be titanium. For the image intensifier to work efficiently, we want all electrons to be converted to light at the output phosphor, correct? And so any electrons going retrograde or backwards is going to degrade the image. So we want all electrons to either go to the output phosphor to convert to light or be absorbed, okay? And so there's a little piece, not a little, a thin piece, I guess it's a little too, but a thin piece of aluminum or titanium is used for that. And we'll talk a little bit more about that. And then the electrostatic lenses are along the path of the electrons to help focus and draw the electrons from the input phosphor to the output phosphor. Any questions about that? So again, this is a picture. Everybody, do you see this? That's wrong. That should be positive. I don't know if you have that on
That's
there.
how it is on our slide, it's positive.
Did I correct it on
Yeah.
yours? Okay, good. Okay. Okay, this is a picture out of your textbook. So it's the same thing, same kind of diagram. But this is the one out of your book, so you can look at that. Okay, so what makes the image at the output phosphor brighter than at the input phosphor? So one of the things is, which is wonderful about phosphors, in fact, this was the single best thing that was done back in the day to greatly reduce our radiation exposure to our patients, and that was the intensifying screen. Do you know why, in the film screen system, which you have not used, do you know why that greatly reduced patient exposure?
Because it doesn't take a lot of X-ray energy to convert to light,
Very
right?
good. It takes very little X-ray energy to make a lot of light energy on some of these phosphors. So here you have one X-ray photon, here's your input phosphor, and that may create 300 light photons. That was what was great about the film screen system. When intensifying screens were used, to most of the X-ray image, of that image, most of it was made by light, not by X-ray. So it was fabulous. So here's one incident X-ray photon, 300 light photons, hits the photocathode. Those light photons are now, look at the ratio from the light photons to the number of electrons produced. Okay, now, you do not memorize those numbers, and every phosphor would be different, every manufacturer would be different. So it's just an example, just to show you. And then here we have 1,000 electrons hitting the output phosphor, which gives us 3,000 light photons. So just by that conversion along the path. The other thing that helps with this is that these electrons are being accelerated to the output phosphor. What accelerates them? What makes them go faster? The charge on the anode.
The attraction, right?
The attraction, absolutely. So they're being accelerated, so that kinetic energy of those electrons hitting the output phosphor contributes to that also. So not only number, but the speed at which those electrons are being attracted. And this brightness, as a result of this configuration, is called, flux gain. F-L-U-X, flux gain. Increase in brightness due to the multiplication of the light photons. I've seen flux gain, it says increase in brightness due to the acceleration of electrons. Either one, or both, really. This one's out of your book, out of your textbook, so, look at that again. Here, see, this one's a little bit different than the one I showed you. Here's one X-ray photon, 100 light photons here. Bashong says it goes down to 50 electrons, but yet we end up with 30,000 light photons. Who's right, who's wrong, it doesn't matter. You get the idea of what's happening. That's why I don't want you to memorize numbers. Just know that what causes it to be brighter. And then as Mr. Aston stated, minification gain. That is due to the fact that you have that input phosphor. Now, how big is that input phosphor? I'm doing this. How big is it? They can come in different sizes. The size that we have is 12 inches in diameter, okay? 12 inches. And then guess how big the output phosphor is? 1 inch. Okay, so we're taking the light spread over 12 inches, let's say, and concentrating that on 1 inch. So that alone would cause it to be brighter. And that's called the minification gain. Does that make sense? Minify something, make it smaller so the output phosphor is smaller. It's about the size of a quarter, 1 inch in diameter. Okay? So that's the minification gain. So you've got those two things that greatly increase the brightness at that output phosphor. We can talk in terms of brightness. Overall brightness gain is just a combination of the two. So someone's trying to sell you a fluoroscopy tube. You can talk stats with them. Or specs, I should say specs, not stats. Okay, so someone's going to sell you a fluoro tube, and they're going to say, oh, the brightness gain is a gazillion. And so what do the numbers mean to you? If they say, oh, the brightness gain is 4,000, the brightness gain is 10,000. What does that mean to you? Nothing. Just know that the higher the number, the brighter it's supposed to be. So, what does 4,000 mean or 10,000 mean until you compare it to another system, right? You would get your reps and go, Philips, how bright is yours? Or Philips may have several fluoro tubes that have, different degrees of brightness. What are we doing? Are we at a hospital? Is this a podiatrist office? Is this a pain management? What are we doing? Do we need the brightest or do we just need enough? So that depends. So, or they can say, oh, the minification gain is this, or oh, the flux gain is that. So, what is it you really want to know? You want to know how bright the II tube is, right? Or how much brightness it's going to produce, right? But you need to know. They can tell you, oh, they'll sell it to you. Oh, yes, it's a gazillion. There's no units, just a gazillion. Oh, I want that one. That's the one. A gazillion, really? I don't even know how many zeros that is. That's the one I want. Okay, what if it takes a gazillion X-rays to produce that brightness? Now do you want it? No. You want to know, when you buy that fluoro tube, you want to know what the conversion factor is. How much radiation does it take to get a certain amount of brightness? That's what you want to know. So the conversion factor, while it doesn't contribute to the overall brightness like minification gain and flux gain, what the conversion factor will tell you is how much radiation it takes to achieve a certain amount of brightness. So the luminescence at the output phosphor versus the input exposure rate of the radiation. And that, do you know what this is? CD? It's not a round disc that plays music or whatever. This CD is for candelas. So that's a measurement of luminescence. There's other ones, Lambert's, Lux. There's other measurements of luminescence. But in this formula, candela is used. And do you know what M squared is? Make me proud.
Meters?
Meters. Okay, M is meters. But what's meter squared? Length times width?
Me.
Yeah, there you go. It's the area. It's the area. Meter squared is measuring the area. So the amount of luminescence per area, right, versus the input exposure rate of the radiation. So that's milliards per second. Millirentgens, that's the intensity per time. Anytime you have the word rate, time is involved. Whether it's per seconds, minutes, or hours, that's a rate. Okay? If I said, what is radiation exposure measured in, you would just say milli-R. If I said, what is the exposure rate, then you have to say so much radiation per period of time. So you're not gonna have to work that formula. I'm not gonna give you a word problem. You're gonna have word problems, just not that one.